Good evening all of you, and here is a mixed problem of limits and matrices. Usually you will see in the sequence of matrices, higher power of matrices is asked, and it's one of the good problem where the basic idea of limit is combined with the idea of matrices. So let's go about it. It's given a matrix M which is 3 cross 3 and we have X as a column matrix or column vector to say. We need to find the limiting value of the sequence of matrix M raised to the power n X where n is a natural number. Now a usual typical way to start the solution method one will be to try to get some pattern. So we have mn, we'll try to calculate mx, we'll do with m square x, m cube x and hope for some pattern soon. So this is left as an exercise for you. I'm going to give you a smart way of doing this. Okay, so method smart. So first thing in this kind of problem, you try to observe something. For example, here what about the sum of this row? So clearly sum of this row is something which is not 1. Now why I thought of sum of rows to be 1? Because if sum of row is 1, then maybe this matrix M will have a special property. For example, let's say this row summation becomes 1. Then if I multiply this with 1, 1, 1, it's still going to be 1, 1, 1. And this I have already discussed in one of my video lecture. So okay. Because if you multiply this row vector with this column vector, the dot product will produce still 1. Because let's say if it is A, B, C, since matrix has a property A plus B plus C equals 1, the sum of row element, hence it will automatically give 1. It means if let's call this matrix as some crazy matrix C, so crazy matrix times I matrix, if I call I as this 1, 1, 1, that will still give I matrix here, right? So in fact, now I can pre-multiply with C. So C square I will still be Ci and Ci is still I. So in fact, it will be true for C ka power any natural number n times I will be I. It means sum of row element of even the nth power of this crazy matrix will still be 1. Although the element distribution will change, but the sum will be invariant. Okay, so that's the usual deal in this kind of problem. That's why I doubted, because in the last column, we can clearly see sum of this element is 1. But soon we are having a bad day because this is not going to be 1 and same this is not going to be. But there is again something special about this matrix. All these are in the powers of 2. In fact, 1 is also 1 by 2 ka power 0 and 2 is 1 by 2 to the power infinity. Like this tends to 0 and this tends to 1, right? So in that sense, all of them are power of 2. Okay, so maybe we'll try to react this 1 by 4, 1 by 8, 1 by 16, 0, half, 1 by 4, 0, 0, 1. And why don't you try to multiply with something which still goes into power of 4? The reason being so that I have a control like where it's going when n is 0. And the best matrix that we can think of is what if I multiply with 1? Okay, so let's multiply with some column vectors like I cap 1, 0, 0. You could try with 0, 1, 0 and 0, 0, 1. So that's the thought process. So of course, if I do so, so this guy multiplied with this is gonna give me 1 by 4. This with this, that will die, and again the third will die, right? So what I've seen is m times 1, 0, 0 is gonna give me 1 by 4, 0, 0. What about m square? So what if I further multiply this with m? So m square times 1, 0, 0. This I can pre-multiply with, again we have 1 by 4, 0, 0. That will react with 1 by 4, 1 by 8, 1 by 16, and rest term is as it is. So clearly the only difference that will be produced when this first term is multiplied with first term of this column vector, right? First term of row vector hits first term of column vector. So that will give me 1 by 4 square, again 0, 0. And now you can see with induction, you can clearly see m ka power n, 1, 0, 0. That's gonna give me 1 by 4 ka power n, 0, 0. And that's a good news. Because now I know when n is tending to infinity, this column vector is going to be a 0, 0, 0 matrix, right? So that's the cool thing. With this cool thing, what we can do is we can possibly segregate 2, 3, 6 into 2 matrices. One matrix which is 1, 0, 0 because that's helping us, and other matrix that we are having is, of course, leftover will be 1, 3, 6. Still there is a lot to go, because until unless 1, 3, 6 doesn't possess some special property, it's going to be definitely difficult for us to you know, like attack the question in a natural way. So maybe if that doesn't come, then again we'll try to split 136 as 100 plus something left over, or 010 plus something left over, so as to get some rhythm and a strong pattern in this. So let's try with again now our new friend 136, right? And let's react matrix M with 136, and that gives 1 by 4, 1 by 8, 1 by 16, 0 half, 1 by 4, 0 0 1. This got multiplied with 1, 3 and 6. So let's see what we got. So first row will be reacted with first factor. So that gives me 1 by 4 plus 3 by 8 plus 6 by 16, which goes to 3 by 8 is nothing but 6 by 16, and that's going to 4 by 16. And that's a surprising result because it's a stage at 1. 6 plus 4 is 10, 10 plus 16, 16 by 16. What about when this second row reacts with second row? So you can see 1 goes with 0, 3 by 2 plus 6 by 4, and that's surprisingly 3. What about last guy? Last guy is 6. And this exactly happened what we wanted it to happen, right? Because instead of 111, now we have found another guy. Instead of 111, which I doubted in the beginning about that crazy matrix, I found another guy 136 which possesses a magnificent properties. And the beautiful property of this matrix is M times this new matrix, let's call Y, is going to give Y. So what about if I pre-multiply this with M? So this is going to give me M times Y. And from here to here I have used associative property of matrix where AB times C is same as A times BC. And that's why in matrix you can write just with the symbol ABC, where it doesn't matter, okay, how you read it. ABC is same as A times BC. Remember, matrix doesn't possess a symmetric property, but matrix are not commutative, but they are associative. That's crazily true. And this equals My, and that gives me M square Y equals My, and My is by default Y. So now you can see again if we'll take M on both sides, we are going to get M cube Y equals My, and Y is back to M. That shows like M to the power Ny will be M for all n belonging to natural number. And now that solves the problem, because we have a special reaction of matrix M with Y. We have a special reaction of matrix M with column vector 1 0 0. So now according to the question, we wanted to find M to the power nx. So that is nothing but M to the power n, and x is segregated into 1 0 0 matrix plus remaining 1 3 6 matrix, right? 1 3 6, which is Y. So we have n to the power n by distributive property of matrix 1 0 0 plus m to the power ny. Now let's take limit when n tends to infinity, m ka power nx. So this will give a column vector. Limit of sum is sum of limit here, because all these both term is finite, hence I am allowed to use it. 1 0 0 plus limit n tends to infinity, m to the power ny. And this quantity, as we have already seen, this goes to simply 1 by 4 ka power n 0 0 limit n tends to infinity plus m to the power ny goes back to y. So limit n tends to infinity, it is just y. And since this quantity is going to die, so it will become 0 0 0 plus 1 3 6. And the answer for this beautiful problem is stage at 1 3 6. So in the limiting case, the column vector that we are getting is nothing but it's simply matrix 1 3 and 6 is our final answer to this problem. So I hope you enjoyed the question and you have seen like how basic observations can help you to reach the answer in a very good way, right? So the takeaway from this today's class was, when you have higher power of matrices, especially when sum of row and sum of column is 1, you can take this magical advantage by inviting a guy which stays invariant during the process. Thank you. Have a good day.